Let's start with a strange reality inside modern processors. Your CPU is constantly making mistakes, not small mistakes, massive architectural mistakes. Every single second, a modern processor executes thousands, sometimes millions of instructions that will never actually happen. Instructions that will be erased, discarded, rolled back, completely undone. And yet, despite constantly guessing wrong, modern CPUs still produce perfectly correct results. Your programs run correctly. Your operating system behaves normally. Your files remain intact. So the obvious question is this: how does a CPU undo work that already happened? How does a processor reverse instructions that were already executed? How can it rewind the machine state back to a previous moment? And how does it do this hundreds of times per second without you ever noticing? To understand that, we need to explore one of the most important and least understood systems inside modern CPU architecture: rollback and recovery. Because modern CPUs are not simple machines that execute instructions one by one. They are speculative machines, predictive machines. They run ahead of the program trying to guess the future, and when the guess is wrong, they must rewind time. The fundamental problem. Let's begin with the core issue. Modern CPUs execute instructions out of order. Instead of waiting for earlier instructions to finish, the processor allows later instructions to run first if their inputs are ready. This dramatically increases performance, but it introduces a dangerous problem. The CPU is now executing instructions before it knows whether they should execute at all. For example, if X lies 0, A plus B, the processor does not want to sit idle while waiting for the condition X larnel to be evaluated, so it predicts the outcome. If the branch predictor believes the condition will be true, the CPU will immediately begin executing A plus B before the branch condition is actually resolved. Here, Drews, this is called speculative execution, and it happens constantly, but sometimes the prediction is wrong. Maybe X was actually negative. That means the instruction UAGAB should never have executed. But the CPU already ran it. So what now? The processor must erase everything that happened after the incorrect prediction. This is where rollback and recovery mechanisms come in. Speculation is allowed, but only temporarily. The key principle of modern CPU design is this: speculative work is allowed, but it is not immediately permanent. When instructions execute speculatively, their results are not written directly to the architectural state. Architectural state includes your architectural registers,
flash memory,
program counter,
visible processor state.
Instead, speculative results are stored in temporary structures. That these structures allow the CPU to delay commitment until it knows that execution was correct. Think of it like writing on a whiteboard instead of carving into stone. If the speculation turns out to be wrong, the CPU simply wipes the board clean. Nothing permanent was changed. The structures that enable rollback. Modern processors maintain several internal systems that make rollback possible. The most important are reorder buffer, ROB, register renaming table,
physical register file,
load store buffers, branch checkpoints. Together, these form the speculative execution environment. Let's examine what role each one plays in recovery. The reorder buffer, the safety net. The reorder buffer, or ROB, is the central mechanism that allows the CPU to undo mistakes. Every instruction that enters the out-of-order engine receives an entry in the ROB. That entry tracks instruction completion, destination register, result value,
Exception status,
there's some branch outcome, and even if instructions execute out of order, they must retire in program order. The reorder buffer enforces this. Think of the ROB as a commit queue. Instructions execute early, but they only become permanent when they reach the head of the ROB and retire. Until then, their results remain speculative. If something goes wrong before retirement, such as a branch misprediction, the CPU can simply discard all younger ROB entries. This instantly erases the incorrect speculative work. Branch misprediction, the most common rollback event. The most frequent reason for rollback is branch misprediction. Remember, branch predictors attempt to guess the outcome of conditional branches. They are very good. Modern predictors exceed 95% accuracy, but even a small percentage of mistakes can cause many rollbacks. Imagine this instruction sequence. 1, CMPX, 0, 2, jail skip.
Nice.
R1, R2.
All R3, R4, the skip. The CPU predicts the branch, Suppose it predicts the branch not taken.
So it begins executing instructions 3 and 4 immediately.
But later the comparison resolves. The CPU discovers the branch should have been taken. This means instructions 3 and 4 should never have executed. The processor must now perform recovery. Here is what happens internally. Step 1. Detecting the mistake. When the branch instruction executes, its real outcome becomes known. The CPU compares this outcome with the prediction. If they match, execution continues normally, but if they differ, the CPU detects a misprediction event. At that moment, the processor knows that everything after the branch is speculative and incorrect. Now recovery begins. Step 2, pipeline flush. The first visible step is a pipeline flush. All instructions younger than the mispredicted branch are removed from the pipeline. This includes instructions in stages such as decode, rename,
Dispart the BPMAs. Dispart a BPMAs.
Ori, issue. These instructions are simply invalidated. They will never retire. The CPU stops issuing them and removes them from the execution machinery. But that alone is not enough, because speculative results already exist in internal structures. Those must also be undone. Step 3, reorder buffer rollback. Next, the CPU rolls back the reorder buffer. All ROB entries younger than the mispredicted branch are invalidated. Their results are discarded because those instructions never reach retirement, their results never become architectural state. It is as if they never happened. This is why the reorder buffer is so important. It acts as a commit gate. Nothing becomes permanent until it reaches the front of the ROB. Step 4, register renaming recovery. Now we encounter one of the most subtle parts of CPU recovery. Register renaming. Earlier in the pipeline, instructions are mapped from architectural registers to physical registers. For example, Rexroom P70, RBX, DRO P42. Every time an instruction writes to a register, a new physical register is allocated. This prevents false dependencies, but when rollback happens, the CPU must restore the previous register mapping. Otherwise, the architectural state would become corrupted. To solve this, CPUs maintain rename checkpoints. When a branch instruction is renamed, the processor saves the current register mapping state. If the branch later mispredicts, the CPU simply restores the checkpoint. This instantly returns the register mapping to the correct earlier version. It is effectively a snapshot restore of the register state. Step 5, freeing physical registers. Speculative instructions allocate physical registers. When those instructions are rolled back, those registers must be freed. Otherwise, the processor would eventually run out of registers. The recovery system returns those registers to the free list. This makes them available for future instructions. Again, the reorder buffer helps track which registers belong to speculative instructions. Step 6, restart execution. After rollback completes, the CPU must resume execution from the correct point. That point is the true target of the branch. The fetch unit redirects instruction fetch to the correct address. The pipeline begins filling again with new instructions. Execution continues as if the incorrect path never existed. That the entire process, detection, flush, restore, restart, may take only a few dozen cycles. On a multi-gigahertz CPU, that is a tiny fraction of a microsecond. Why rollback is so fast? At first glance, rollback sounds expensive, and in some ways it is. Branch mispredictions cause real performance penalties, but CPUs are designed to recover extremely quickly. Several design principles make this possible. First, speculative results are isolated. They do not overwrite architectural state immediately. Second, the reorder buffer maintains precise ordering. Third, register renaming checkpoints allow instant mapping restoration. Fourth, pipelines can be flushed rapidly. Because of this, recovery is usually much cheaper than waiting for perfect certainty before executing instructions. Speculation wins. Even though mistakes occur, exceptions and precise state. Rollback is not only used for branch mispredictions, it is also essential for exceptions and interrupts. Imagine this instruction, DVR1, R2. If R2 is 0, a divide by 0 exception occurs. But modern CPUs may have already executed many later instructions out of order. Those instructions must not appear to have executed before the exception. The system must maintain precise exceptions. Well, this means the processor must appear as if instructions executed strictly in order. Rollback mechanisms ensure this. When an exception occurs, all younger speculative instructions are discarded. The CPU rolls back to the instruction that caused the exception.
Then the operating system handles the event.
From the software's perspective, execution still appears perfectly sequential. Memory speculation and recovery. Branches are not the only speculation source. Memory operations also speculate. For example, the CPU may execute a load before an earlier store whose address is not yet known. Well, this is called memory disambiguation, but sometimes the guess is wrong. If a load executes before a store that actually writes to the same address, the load must be invalidated. This triggers another rollback scenario. The CPU detects the memory ordering violation. Then it flushes the younger instructions and restarts execution. Again, speculative work is undone. Checkpointing multiple branches. Modern processors may speculate across multiple unresolved branches simultaneously, and this means several checkpoints may exist at once. Each branch creates a potential recovery point. If the youngest branch mispredicts, the CPU restores the latest checkpoint. If an older branch mispredicts, even more speculative work may need to be discarded. Managing these checkpoints efficiently is one of the hardest problems in CPU design. The processor must balance speculation depth, hardware complexity, recovery latency. Too many checkpoints increase hardware cost. Too few limit speculation. The illusion of sequential execution. From the programmer's perspective, none of this complexity is visible. Wizard software believes instructions execute strictly in order. One instruction completes. Then the next, but inside the CPU, hundreds of instructions may be in flight simultaneously, speculating, executing early, being undone, being restarted. Rollback mechanisms maintain the illusion of sequential execution. Without them, out-of-order execution would break program correctness. The cost of mistake, even though rollback is fast, it still has a cost. A branch misprediction typically costs 10 to 20 cycles on simple CPUs, and sometimes 20 to 30 plus cycles on deep pipelines. During recovery, pipeline stages empty, instruction fetch restarts, execution resources idle temporarily. This is why branch prediction accuracy is so critical. The better the predictor, the fewer rollbacks occur.
And the faster the program runs.
Modern CPU design is built around recovery. One of the most surprising truths about modern processors is this: they are designed assuming mistakes will happen constantly.
Speculation is aggressive.
Execution runs ahead. Predictions guide the machine. Rollback mechanisms ensure correctness when predictions fail. In a sense, modern CPUs are not deterministic machines. They are probabilistic machines with safety nets. The architecture assumes the future will be guessed, sometimes correctly, sometimes incorrectly, but always recoverably. The big picture. Let's recap what happens when the CPU makes a mistake. First, speculative instructions execute. Then a misprediction or violation is detected. The pipeline is flushed. The reorder buffer discards younger instructions. Register mappings are restored from checkpoints. Physical registers are freed. Instruction fetch restarts from the correct address, and execution continues. All of this happens in a fraction of a microsecond. The program never notices. The illusion of perfect sequential execution remains intact. Final thought: modern CPUs are among the most complex machines humans have ever built. Billions of transistors cooperate to execute instructions correctly. But much of their work involves undoing things that should never have happened. Speculative instructions, incorrect branches, misordered memory operations. All of it must be recoverable. Rollback and recovery systems make this possible. They allow processors to move forward aggressively while always keeping a way to rewind the past. And without this ability to undo mistakes, the incredible performance of modern CPUs simply would not exist.